Hello, my name is Minkun Kim. I'm a PhD student at Adopt Center in Dublin City University. My work is supervised by Professor Martin Crane and Dr. Marija Bezbradica. The title of my talk is Claim Count Prediction with Over-Dispersed Outcome and Mismeasured Covariates in Actuarial Practice. I'm going to start by giving you a rough outline of my study. I begin with introducing some problems in the claim count prediction task for actual practice and answering research questions. I'm moving on to my idea of the modeling approach to tackle the problems I introduced, and then briefly touch the model selection and evaluation technique. I finish up this PowerPoint with numerical math examples and discussion. I'm going to start with introducing some important actuarial process to manage business loss. Let's say the capital S is aggregate claim loss, which is insurer's main concern. It is important first step to estimate how many claims will be reported. As it is a count prediction problem, one might think of Poisson regression, but there are some problems that throw this conventional model into question, which is over-dispersed outcome and mismeasured covariate. These two problems are very common in practice because of the presence of unobservable covariate brings correlation into outcome, and the complex data collection practice contaminate the given covariate. In this regard, my research question is how to approach the claim count prediction, tackling both problems simultaneously. So my modeling approach is negative binomial generalized linear mixture model based on combinational hierarchical base and CMAX framework. In a nutshell, the hierarchical base helps capture subtle variations with multiple levels of the aggregation system in parameter space and data space, while CMAX captures the trend of noise, then reduces it by discovering the point where noise becomes zero. To our knowledge, the combination of these two frameworks has not been studied before, and we connect these two approaches by bringing the CMAX into the Gibbs sampling in the inference process for hierarchical Bayesian negative binomial GLMM framework. This shows a series of parameterization details for prior and posterior densities, from where we can obtain the samples for parameter inference for the GLMM. And this shows the basic idea of CMAX extrapolation, describing the relation between data contamination level and the estimation of target parameter. So our modeling approach is evaluated by comparison with other rival models. And as for the evaluation metric, we choose Watanabe AIC over just regular AIC or BIC because our main parameters, slope, intercept, dispersion, do not necessarily follow Gaussian. And unlike just regular AIC, Watanabe AIC eliminates the distributional constraint and assess overfitting at the level of individual observation. So the chart A, a histogram of the outcome variable y, which is absent count distribution, and the table B is a summary descriptions of selected. And on the right hand side, the table shows the result of the conventional naive GLM analysis for absence hour count with error-prone covariate. And note that only significant covariate results are presented. So now the out-of-sample prediction performance of our hybrid Bayesian approach is compared with conventional models such as naive GLM and CMAX model. We use three different model fit evaluation metrics, such as mean square logarithmic error, scaled deviance, and Watanabe AIC. As you can see, it is apparent from the box plot that our model, which is hierarchical Bayes and CMAX combination, leads to more improvement in model fit than the case with CMAX only. The measurement error correction with CMAX clearly abates the bias and improves model fit, but the hierarchical base brings a more significant bias reduction, exhibiting dramatically smaller deviances and a narrow range of variance compared to the with other plain CMAX and GLM model. This observation becomes even more clear when we use advanced metrics such as Watanabe AIC that accounts for the risk of overfitting. So if visualizing the out-of-sample prediction result on each 36 employees expected absent hour count, one can observe that overall variation of group mean estimate is reduced. If the distinct value of each employee's expected absent hour count can represent unique identity of each employee, the implication of reduced variation as a result of estimation regularization is that our hybrid model captures certain information running across different individuals, which reduces the bias problem triggered by of dispersed outcome and mismeasured covariate. The series of plots given here succinctly illustrate the prior setting based on CMAX and its posterior computation result for the major GLM parameters, which is varying intercept, varying slope, and the dispersion, so which are simulated through Monte Carlo algorithm within the hierarchical Bayes framework. Here we compare the two hierarchical Bayesian GLM with and without CMAX. The first two plots on the top shows the amount of correlation between the varying slope and intercept learned by each hierarchical Bayes model, and both lands on reasonably high and negative correlation values. The other two scatter plot on the bottom displays 36 pairs of intercept and slope estimates that shrunk toward the global mean, keeping the variability between the cohorts intact. This is because the hierarchical Bayesian GLM simultaneously estimate both the intercept for each cohort and the variation among cohorts by modeling their covariance. The point here is that although both hierarchical Bayesian models discovered unobservable information that can redefine the relationship between each cohort, the model integrated with CMAX captures much more of the information as a result of error correction in the covariate. One can say that CMAX-based hierarchical model can learn this correlation much deeper, thus can model the data better by reducing the bias and improving the model fit. There are several limitations to this study. Above all, we need to reinforce the theoretical foundation in terms of specification of measurement error setting, optimization of the hyperparameters, and the development of proper extrapolation curves for CMAX. From the perspective of insurance application, we should consider the extension of predictive tasks for claim count with other external information, such as benefit claim amount or loss, etc. Some absent cases do not necessarily turn into benefit claims, as the insurance company can refuse the claims when the cases do not meet their criteria. By matching the absence count prediction with the actual loss, a company can make better interpretation of the risk distribution tails or extreme values or investigate conversion rate that would be directly translated into future claim expenses.